Welcome everyone to Young Researchers Colloquium. Our speaker today is Krzysztof Bardadyn, who will tell us about system algebraic approach to spectral analysis of weighted composition operators. Please go ahead.
Okay. First, I would like to thanks to the organizers for inviting me to give a talk for you. It's a great honor for me. I know you are working in different areas of mathematics, so let me start by give you some base definitions. Okay, today I will talk about system algebraic methods which are helpful to study the spectrum of some class of operators. So I recall that system algebra is Banach algebra with some additional anti-linear involution satisfying these relations. I recall that Banach algebra is complete normed algebra where multiplication is continuous. And I think the most important examples of system algebra as follows are false. The first one is system algebra of bounded operators on some Hilbert space H with standard operator norm and where star is Hermitian conjugation. The second one is system algebra of continuous functions on some compact Hausdorff space X, where norm is supreme norm and star is a complex conjugation of function. These examples are important due to the following theorems. The first says that any system algebra can be embedded in system algebra of bounded operators on some Hilbert space H. I think I should give you some explanation. It's known that any star monomorphism between system algebra is automatically isometric, and since range of isometry is closed, the image of any system algebra over star monomorphism is system algebra also. So we see that we can treat any system algebra as some system subalgebra of B of H. And the second one theorem says that any system algebra is isomorphic to system algebra of continuous function. Every unital system algebra and commutative system algebra is isomorphic to system algebra of continuous functions on some compact Hausdorff space X. This space is unique up to homeomorphism. It follows from Stone-Banach theorem. And I recall the spectrum is the set of complex numbers such that this operator is non-invertible. It's a known fact that the spectrum of operator does not depend on the system algebra contains it. In fact, if you want to know spectrum of bounded operator, it is sufficient to look on its spectrum just only in system algebra it generates by it. Let's start by application of Coburn theorem. Coburn theorem says that for every system for any non-invertible isometry, system algebra generated by T is isomorphic to Teplitz algebra. The Toeplitz algebra is important and famous. It is exactly sister algebra generated by one-sided shift of L2 of n, on L2 of n. It is easy and standard exercise to check that the spectrum of one-sided shift is unit disk, and because this algebra generated by any non-invertible isometry and is isometric to Toeplitz algebra, and spectrum of operator does not depend on whole B of H, just on depend just on C-star algebra generated by this operator, we obtain that the spectrum of any non-invertible isometry is unit disk. And Halmos calculated spectrum of weighted shifts for any weighted shifts. Weighted shift is operator of this form, where T is one-sided shift and A is operator of multiplication by some bounded sequence. And he stated that there is no well-developed theory for more general classes of weighted shifts. And what my goal is to give you some proposition of that theory.
Sorry.
Yeah.
Can you recall once again what is the sigma algebra generated by an operator? I mean, what is the C star of T?
C star of T is the smallest C star algebra
Okay.
contained with T. Yeah.
In what?
It is the smallest C star algebra. In what? In B of H, some B of H. You have some space, Hilbert space H,
okay,
and non-invertible isometry, and you can generate C-star algebra by T in this bigger C-star algebra.
Okay.
So let me pass to the second example, which give us some motivation. Let X be the space of sequences with an entries from 1 to n, and let phi be shift be the shift on this space. Let H be Hilbert space associated to Bernoulli measure. What is important here? Important is that Bernoulli measure is phi invariant. You can take any different phi invariant measure, and it will be work. It will be work. In fact, important is that this measure has full support. But to simplicity, but when phi is when mu is phi invariant, then operator of composition is isometry, and the picture is more simple then. We can identify C star C of X with algebra of operator of multiplications by multiplication by continuous functions, continuous functions, and then C star algebra generated by AT, its weighted composition operator, is isomorphic to Cuntz algebra. I think Cuntz algebra is the most famous C star algebra in the world. It is exactly Cuntz algebra. The definition is Cuntz algebra is universal C star algebra generated by n isometries, which projections range sum up to 1. And Cuntz proved that this C star algebra is simple, and up to isomorphism it is unique. Should I explain what means universality? Okay. So this isomorphism given by these maps. The question is, how does the spectrum of weighted compositions looks? And I recall that Cuntz algebra has a gauge action. A gauge action is an action of circle unit circle group on C star of IT, and it is given by in this way. It is identity on A, and it's scaling T by Z. And existence of gauge action implies that spectrum is rotation invariant. And this is in computation show us it. If something is not in the spectrum, then of course this operator is invertible, and since gamma z is automorphic, this is invertible also. By definition of gamma z, it is equal this, and it is equivalent that z bar lambda not lies in the spectrum. Hence, spectrum is invariant under rotation around 0. So we have one nice property of C-star algebra, which implies which give us some information about the spectrum. The second one is simplicity. Cuntz algebra is simple, and then spectrum of AT and essential spectrum of AT coincide. I recall that simplicity means that there is no non-trivial two-sided closed ideal. And yes, because this C-star algebra is simple, it has no any non-empty, non-zero compact operator. Okay, I think I should recall what is essential spectrum. Essential spectrum is the set of such complex lambdas such that lambda minus AT is not Fredholm operator, and the Fredholm operator is some generalization of invertible operator. It is invertible operator modulo some compact. And because this intersection is 0, invertibility in C-star of AT and in this quotient, its calculus algebra, is equivalent. So essential spectrum and spectrum coincide. Another property of C-star algebra, maximal, A is maximal abelian, and this implies that spectrum is connected. A is maximal abelian. It means that if something commutes with any element of A, then it must be in A. We cannot add to A some other operator and obtain commutative algebra. And to show it and prove it is a little harder. To do this, we need to use some classic tool like risk projections. And I give you some scratch of this proof. One can be shown that this risk projection correspond the component of spectrum which is contained in a unit disk commutes with any elements of A, and then it must be in A, So it is a characteristic function of some phi invariant set, and by irreducibility of this dynamical system, we get that there is only one component of spectrum. So in this case, the spectrum must be a disk. And basing on our knowledge from thermodynamical formalism, we can deduce a formula onto spectral radius. It is the last component to full full description of the spectrum. And the spectral radius is square root of topological pressure. It is given by this formula. This is topological pressure, where maximum is taking over all ergodic measures. So we have nice three properties of C-star algebra, which allow us to describe the spectrum of weighted shift operators, and some facts from thermodynamical formalism which allow us to compute the spectral radius of AT. And now we want to build the general theory, where we can study spectral radius, spectrum of weighted shifts in this way.
Would you say something more about this last formula?
This last formula, okay.
Yes, what it appears.
What do you say?
Some intuition behind it, how it appears. If it is possible.
Oh, it's intuitions. I'm not sure, but this H is Kolmogorov-Sinai entropy here. I should say it. I think I will talk. I will say about it something more later. Okay.
Okay.
I will talk about it. But I don't think I will give you. I think I don't. I will not give you intuition about it. But this okay. I will tell something more about it later. I promise. Okay. So now we want to associate C-star algebra to a local homeomorphism, which give us a dynamical system on some space. I will assume that throughout my talk, I will assume that phi is local homeomorphism on a compact Hausdorff space, and then we get endomorphism alpha. It is composition with phi. In fact, any unital endomorphism of C of x has this form. It is composition with some continuous map, and we will need to notion of transfer operator. A transfer operator is a positive linear operator satisfying this formula. This formula implies that if L is unital, then L is left inverse of alpha. And in this way, Pełczyński, when he described operators on spaces, Banach spaces of continuous functions, he used such operators to give some analogus of inverse for non-invertible endomorphisms. Moreover, this operator is important in dynamical systems, and it codes some dynamical properties of phi. Under our assumption about phi, we know that every transfer operator has this form. It is some kind of average, and this sum is always finite, because if phi is local homeomorphism and X is compact, then any preimage of phi must be finite. In fact, choosing a transfer operator the choice of transfer operator is a choice of such a map rho. If we take any continuous function rho, then this formula defines a transfer operator for phi or alpha. This corresponds. And for simplicity, we will assume that rho is strictly positive. We can, and every results I will present can be proved without this assumption, but the picture will be not such a nice. Okay.
Sorry.
Mm-hmm.
Can you tell like how this arises, like rho of X?
Oh, it's, yes. Okay. Yeah, I can. By Riest theorem. This is positive. This is, if we fix y, then we obtain positive functional on C of X, and then for any y we have measure, which yeah, you know, like in Riest theorem. And by this relation, one can be showed as the support of this measure is contained in preimage of is contained in phi to -1 of y. And because our fibers are discrete, then we have some here. And in fact, rho of X is some measure on singletons here.
Okay, I think I tried to figure it out. Yes.
Yeah, and this is star weak continuous, and then with rho is continuous in this. Okay, but maybe I can say it. If we leave left assumption that rho is continuous, then the theory is more complicated. But we have some knowledge about relationship between zero and non-continuity points, and meaning this point for phi. We have some relation. It is some relation between it, but it will be more complicated. Okay, let's define auxiliary functions in this way. I think I can skip these comments because it's easy. And we define cross product of C of X by transfer operator L as universal C-star algebra generated by C of X and some operator or symbol T. Subject to this relation. This relation called a transfer operator in our system in cross product, and this is some kind of Cuntz relation. For any local homeomorphism, we can find this function, so we can embed our C-star algebra. Okay. This is no empty relations because these functions exist. And the following theorem, we remember that maximality of C of X plays an important role in study of the spectrum. And this theorem gives us some nice characterizations on maximality. Two says that C of X is maximal abelian subalgebra of cross product if and only phi is topologically free. Phi is topologically free if and only if the set of periodic points is boundary. It has empty interior. And 3 says that it is that maximality is equivalent to fact that C of X detects ideal in cross product. C of X detects ideal in cross product if and only if for any non-zero ideal in cross product, if any non-zero ideal in cross product has non-zero intersection with C of X. It means that C of X detects ideals in cross product. Okay, so now let me pass to the main object of our research, the abstract weighted shifts. We will assume that T is some bounded operator and A is unital commutative C-star algebra, subalgebra of B of H. And we'll assume that we will assume following axioms. A1 says that A is invariant under conjugacy by T. A2 give us unital endomorphism such that this commutation relation holds. And A3 is some kind of non-degeneracy condition. We can identify, and if these axioms hold, then operator of form AT we will call abstract weighted shift operator. We call abstract weighted shift operator. Okay, we can identify A with C-star algebra of continuous functions on some compact Hausdorff space X, and then alpha is given by composition with some continuous map phi, and we will assume that phi is local homeomorphism. Moreover, A2 and A3 says that imply that conjugacy by T give a transfer operator for alpha. So it has this form for some continuous non-negative function rho, and A3 implies that the rho is positive on the dense set, but I will assume that is strictly positive function. A1, A, and 2 give us the nice description of structure of C-star of AT. The set of elements of this form is linear dense, and A3 give us existence of n functions, positive elements of A, such that this Cuntz relation holds. So we see that by this we see that there is natural star epimorphism from cross product onto C-star algebra generated by AT, by abstract weighted shift operators. And natural question is when this epimorphism is isomorphism. And the answer is if phi is topologically free, then cross product is isomorphic to C-star of AT. So by previous theorem, we get that A is maximal abelian subalgebra of C-star of AT. A detects ideals in C-star of AT, and there is gauge action in C star of AT. Existence of this action can be shown in similar way as in Cuntz algebras. So we obtain corollary if we assume that AT is abstract-weighted shift operators and phi is topological free, then spectrum is rotation invariant, and it is union of some disk and some number of annuli. Moreover, if A has zero intersection with compact operators, then spectrum of AT and essential spectrum of AT coincides. So this implication can be shown that in the same way as in this case of Cuntz algebra. And because since A detects ideals in C star of AT, we have this implication because we have if A intersection of A and compacts is 0, then C star of AT has no non-zero compact operator, and then the spectrums coincide. It's not hard to do, but we can show that if X has no isolated points, then then intersection of A and compact operators is 0. So the following lemma give us more detailed description of spectrum. If the intersection of spectrum and unit circle is empty, then P is the risk projector correspond the component of spectrum which is contained in unit disk. The risk projector is operator such that it is idempotent, and the spectrum of AT restricted to range of risk projector, this operator P, this spectrum is equal to the spectrum of the component of AT which is contained in unit disk. This is exactly risk projector. This is definition. And then risk projector commutes with any elements of A. So because A is maximal abelian, P, since A is maximal abelian, P must be in A. So it is characteristic function of some set, Klopen set, in fact. And then phi restricted to completion of x1 is homeomorphism onto x2. X2 is phi invariant. And this gives us description, because if space X is connected, then there is one component of spectrum. This lemma says it. The connected space, if X is connected, then the spectrum it has one component. Okay, so to full description of spectrum, we want to know spectral radius. This is the last component of our knowledge about spectrum. And I will start by invertible case when phi is homeomorphism. It is old result that if phi is homeomorphism, then logarithm of spectral radius of AT is given by this formula, where maximum is taking over all phi invariant probabilistic measures, and it is equal when we will take maximum over ergodic measures. In fact, this theorem says that this maximum is attained in extreme point. Okay, to say something more about spectrum in non-invertible case, we need to assume something more about phi. We will assume that phi is expanding map. Expanding map is a map is expanding. Map is expanding when for sufficiently close points, the images are far apart. Formal definition is written here. Okay, so I want to recall the celebrated Ruel version of Perron-Frobenius theorem. It can be found in the book of Przytycki and Urmański. And this theorem says that if phi is expanding and topologically transitive, the map is topologically transitive in and only if there is a point which orbit is dense. And if B is strictly positive function such that its logarithm is Holder continuous, then spectral radius, the logarithm of spectral radius of Ruel-Perron-Frobenius operator, Ruel-Perron-Frobenius operator is defined here. Then this is equal to this, and it is very similar to previous result, but the Kolmogorov-Sinai entropy appear here. But if phi is homeomorphic, then Kolmogorov-Sinai entropy disappear, is zero. The right side of this equality is topological measure, topological pressure, and this was defined as David Ruel when he was building thermodynamical formalism, and this maximum is attained in a unique measure, which is called Gibbs measure. In fact, existence of Gibbs measure is shown by this formula. This can be served as a definition of Gibbs measure. So Jacek, it's some intuition, but it's physically intuition, I think. I'm not sure that it is helpful to find this measure where this maximum is attained. So what we did with Bartosz is we generalized this formula for any expanding map. We just assume only that phi is expanding and B is non-negative continuous function. A lot of authors obtained this kind of results, but always they assume that that phi is topologically mixing or something equivalent version of topologically mixing, and that X is manifold. So this theorem says that we only need that phi is continuous and B is non-negative. We don't assume that any Holder continuity of B, of logarithm B. Yeah, but here we lost the uniqueness of this maximum. Yes, we don't uniqueness. Okay. So why this theorem is important? It is important because it allows us to give formula onto spectral radius of AT. This lemma show relationship between spectral radius of weighted shift operators and topological pressure. In fact, it says that if phi is local homomorphism, then spectral radius of weighted shift operator is square root of spectral radius of Perron-Frobenius operator associated to function a module a square times rho. And the proof is easy. By Gelfand-Neymark formula, it is sufficient to show that n power of norm of a power of at is equal to norm of this of norm of Perron-Frobenius operator. Okay. Okay. By sister equality, we get that norm of square of norm of at is equal to norm of L on L on moduli A square, and by definition of Perron-Frobenius operator, we can see this equality. I'm not sure it's no, it's mistake here. It's pretty clear, but it's not hard. And because L is positive operator, then this is the exactly norm of Perron-Frobenius operator. And another powers can be calculated in the similar way. So I skip it. Okay, so combining this theorem and this lemma, we obtain formula onto logarithm of spectral radius of AT. It is equal to this. Okay. Okay, 15 minutes. So summarizing.
Could you go back to the previous slide? No, the next one.
Okay.
It's the spectral radius of operator L with subscript a squared rho. It is calculated inside the simply Banach algebra of bounded operators on C of X. Yes.
Yes. Yeah.
But it is not a cyst algebra. So do you also have? Oh, okay. You also have
yes.
this spectral radius formula, so that's not a problem. Yes.
The Gelfand formula here, so I'm not sure it's easy, but these results are strictly dynamical. This proof of this theorem don't use any sister algebraic methods.
Okay, that's okay.
But
yes, something.
Yes, if you have abstract weighted shift, and then spectral radius is calculated by Gelfand formula, so it can be harder to show in general Banach algebra, but it will be very important. Okay. So summarizing, if phi is topologically free, then spectrum of weighted shift operator is a union of disk and question. L is not an element in a C-star algebra. Exactly. Okay. Okay. The spectrum of AT is a union of some disk and some number of annuli, and the composition of spectrum give us the decomposition of space X on such complements where disk and some sets where phi is some phi invariant sets. In fact, it's enough. And by Lebediev-Kitover formula, we get formulas on R minus or R plus, because phi is homeomorphism on this. Yeah, spectral radius formula holds in algebra. Yeah. Thus, if X has only one connected, then the spectrum has this form. But it is slightly different here because we have T entropy here. It's something different characterization of phi. Okay, so as corollary, we obtain the following result. If X is expanding and has no isolated points, then the spectrum is disk with and X is connected. Then the spectral radius of is given by this formula. And this proposition show us that if we have a map, expanding map, then we have find a good representation of this map as abstract weighted shifts. So because we have abstract space and some operator satisfying conditions, but the question is if if we have some just a map and we want to find an abstract weighted shifts realizations of this map, and the proposition says that if phi is expanding and has no wandering points, then we can always find such a measure. A measure such that T realize this transfer operator. Okay, I took 20 minutes to last. I think it's good time to questions. So thanks for your attention.
Thank you very much.
Thank you.
Let's clap to thank the speaker. So if anyone has any questions, please go ahead.
So perhaps I have a question regarding the last result.
Mm-hmm.
I understand that just the very, very last, no, the last corollary you had, not the even before, even below. The last slide.
Last slide.
Yes.
Oh, okay.
Proposition.
Yes.
Okay.
Proposition.
So this gives you sufficient conditions, right?
Mm-hmm.
But do you know any results of the type that, well, you start with this phi on the topological space, and when can you say that surely this cannot be realized as an abstract weak shift operator?
Okay, I can explain. If, for example, if phi have wandering points, we need assume that mu has full support.
Okay.
And if we know that in phi invariant, in fact, and we know that the support of measure, phi invariant measure, is contained in is contained in non-wandering points.
Okay, I understand. So,
So
this
we need it, because if we want to have any fine variant measure with full support.
so is this, so just let me read. So is it kind of close to, so this proposition is close to a characterization, right?
Yeah, very close. We can discuss we can discuss what about expanding. And I know that this formula will be not true if phi is this. This assumption is crucial for this formula. But if phi is non-expanding, I'm not sure that we can find. I don't know.
Okay, thank you.
I don't know. This is difference between this proposition and characterization.
Thank you.
Another question?
Were you working with some concrete example of abstract weighted shifts to test your ideas on?
Okay, it's a good question. I had some example of irrational invariance, but you know, the abstract weighted shifts is just a tool. I think you always start with you should always start with concrete map, but an abstract okay. The problem is to find an operator satisfying these three conditions. I think if you want to construct this space and operators, you always have first a map, because you want to because in fact T star has very similar formula as like L. In fact, this L has similar formula as T star, and I think if you want to construct some such operator T, you always have some map, because it's natural. I didn't see abstract weighted shifts without initial map.
Okay.
You asked me that did I work with abstract weighted shifts? Yeah.
Well, I actually asked with what kind of examples you are working with. So I understand that every example came with
Markov shifts. Yes, there is a lot of examples, but Markov shifts can be realizable in this way. Irrational rotation, but it's standard. I had some nice example, but I deleted it. It was Kuntz-Krieger algebra, and it can be it corresponds to Markov shifts, but I deleted it. So, but it's a concrete dynamical system still.
Okay,
I mean that there is can every local homeomorphism give you such such a picture. Be in the case of CK algebra. What does it mean?
So Kuntz-Krieger algebra.
Kuntz-Krieger. In Kuntz-Krieger case, the spec. Okay, maybe I can find this present. Oh yeah, no, I cannot. I cannot. I prepared some slide. There is disk also, but the dynamical system under this picture will be Markov shifts. And then you obtained the description of spectrum of weighted shifts corresponding to Markov shifts. I'm not sure what did you ask for me?
Yeah, so I'm still struggling. I'm thinking already about. I'm thinking like for a long time what this transfer operator. I'm like if you have some example like
transfer operator. You also if okay. A transfer, I can say you what is transfer operator in this case. Transfer operator is if you have countable to one finite to one map, is that map where phi has finite preimage, then you can always define rho as inverse 1 over power of preimage of point. You can always define it in this way. This is always transfer operator. Then and some you take some and you take average standard. I think it's arithmetic average over fibers. If you take rho as 1 over power of the set of preimage, then it is good rho which give you a transfer operator. And in fact, maybe it's worth to mention that this C-star algebra does not depend on positive rho. The problem is when rho is attained zeros. When rho is 0, then this algebra is non-unique. But if L is if you have two transfer operators with positive rho, then the C-star algebra the C-star algebra will be isomorphic. And then if in fact you can write here A cross product A over alpha by alpha.
So do you say that Kuntz-Krieger algebras can be always written as Excel Excel algebras?
Kuntz-Krieger algebra can be written as sorry. Oh, in this way, where T is a composition with Markov shift, and T star is conjugate. Then this C-star algebra will be isomorphic to Kuntz-Krieger algebra.
But the other way around, if you start with Kuntz-Krieger algebras.
Yeah, Markov shift C matrix in Kuntz-Krieger algebra, because this shift allows only it acts on special sequences. So it's C. It's okay.
So do you say that in a way you can build a dynamical system?
Yeah. If you have Kuntz-Krieger, if you have Kuntz-Krieger algebra, then the matrix defined relation in Kuntz-Krieger algebra give you a dynamical system. It is a shift. Yes, it is a shift on some special sequences.
Yes.
Okay.
Yes, I think I see. Yeah. Yeah, thanks a lot.
Do we have more questions?